Okay. So I think I'm live, but the meeting's not quite ready to start yet. We're having a small change of plans. This is a research meeting. I tried not to disrupt research meetings. Why are we going to a different part of the camera? Here we go. I try not to disrupt research meetings. I just want to let them flow. I just want to live stream whatever happens there. So it's hard to plan. So what you're going to see is differential plasticity, but we're going to review another one first, I think, on oscillations, and then go into the differential plasticity. At some point, Jeff has to leave because he has some engagement, and he just wants to hear both of them. I'm not sure how well this is going to work, but I'm just going to put this on my room loop for a minute while they're just setting up. But I wanted to get everything properly set up. So I'll be right with you. I should put like I know there's like a starting soon. Is this it? No. I used to have something said starting soon. We'll move this and just change that to starting soon. Sorry. This is what live streaming is like, so, you know, if you're going to watch this channel, get used to it a little bit. All right, so if I do this now, bing. Yeah, you don't have to pay much attention to that. That's my agenda. It's not like I'm probably not going to stream all of it. I might stream a thing with Chayton later on Twitch. So for those of you just joining, we're going to start as soon as they're ready. But we might start with a different paper than the ones we were talking about. This is a live research meeting, so I just kind of go with the flow here. And here we go. We're getting something. Just a moment. Okay. Okay, I've got a good view, you guys, whenever you're ready. Okay. All right, we're on the air then.
I had the impression that numerically small as opposed to rare.
Yeah,
is that consistent?
the numerically small and many of the possible ones, particularly intralaminar inhibitory to inhibitory connections, don't really exist.
Yeah.
They tend to be inside the same layer. So that is an important thing.
I guess there's an important distinction line between rare and don't.
Yes.
Yes.
There's a slight discrepancy actually also between the electrophysiological and the anatomical data.
Yeah.
But that's an Eastman part of the model that also review actually dealt with exactly that problem.
Okay.
So maybe we will visit that.
Yeah.
Okay, Journal Club time. So we're actually going to do this oscillation paper first, sounds like, and then this will be hopefully very quick. We don't know too much about it, and then we'll switch to this paper. Lucas is going to lead us to this paper.
Roughly, that's good enough, right?
Okay. Well, maybe this whole thing will be really quick. We'll see.
So this paper is old. This is 89.
Yeah, so I just ran across this paper recently, and I thought it was really interesting in light of the Thousand Brains stuff that we talk about. And we've talked a lot about oscillations and synchronizations, but not a lot in terms of cortical columns and how they synchronize and oscillate.
We talked a lot about synchronization with oscillation between thalamus.
Yeah, thalamus and grid cells and hippocampal areas. And so this is and with Florian here, I thought this would be particularly, and I'm sure you know a lot more about this area.
Well, I definitely know Wolf Singer, but
yeah. So this funny coincidence happened. So I want to talk about this, and then the question came up in my mind as I'm reading this in light of our theories. I actually spoke with Peter this morning.
Really?
I asked him my question, so I have an answer from him.
Wow.
Wow. So there we go.
Wow.
But I haven't really had time to reflect. He's basically sent me another paper. So, and this was literally 20 minutes ago.
So he wrote this 30 years ago.
Yeah.
How old is he now?
I don't know how old he is.
100 plus.
That's not the question I asked him.
Okay.
But anyway, so we haven't really talked about oscillations and synchrony within cortical columns. So this paper can be summarized really quickly.
This is between cortical columns.
This is between cortical columns.
columns.
Yeah. Also, I think what he means by column here is mini column, but it's not really clear. He calls it a functional column.
Yeah, that tends to be a
Mini column, yeah, but I think it's still relevant. The basic idea is, let's see if he has a stimuli here. So it's basically oriented bars that's being shown to a cat in V1.
And that's the times.
Yeah, and he's looking at synchrony between columns that are close together and columns that are far apart. And far apart means as far as 7 millimeters away. So 2 to 7 millimeters away. That's what it means by
Pretty
far.
far.
That's pretty far. And so these would definitely be in different cortical columns.
Yeah.
And so the basic thing that he finds is that you can look at the receptive fields, and when they're nearby, and the stimulus is consistent with their preferred orientation, you get some synchrony.
When you say nearby, you talk about how far?
Less than 2 millimeters.
Less than 2 millimeters. That can still be pretty far.
Yeah, it's a big range. It's 0.4 to 2 millimeters.
10.4 is, in many people's books, would be a full
Cortical column, yeah. And I think if you're talking about mini columns, this makes sense, because if you want to find 2 mini columns that have the same orientation,
Yeah, okay.
you probably could go one
So
cortical
he's
column.
not talking about the adjacent mini columns, he's talking about the mini columns that have the same orientation,
Yeah.
some distance away. Okay.
And what they basically find is that if 2 columns are seeing the same stimuli,
Or responding to the same.
responding to the same stimuli, their phases suddenly become really synchronized.
Phase with respect to what oscillation?
You mean like gamma and so on?
Right.
They didn't, I don't think they mentioned that. They just showed that it's really tightly synchronized.
So
you can
now,
look at
let me
the-
understand
you
what
can look at the
That's an
oscillation.
autocorrelogram, and you see the peaks are like, let's see, 50, 10, 20
20,
milliseconds, so that's 50 hertz, so that's low gamma.
Okay.
Right.
Yeah.
I think you mentioned 40, 50 hertz at the top of the paper.
Yeah. I
So-
think that's-
so-
and
So presumably these are representing parts of the retina that are just not the same part of the retina, slightly displaced.
Right.
So does the stimuli, is it like a line that's going across and these are both aligned in the?
So they've done both? So he did both?
But they could be like vertical and vertical, I wouldn't see
Right.
those being activated.
Yeah, so he did both. So one case is you have a bar here and a bar here,
Okay, so that,
and they're moving consistently or not. Or the second case is you have a single bar.
or I was thinking like, it's not like, the other thing you could have is something like this, where you'd have a bar here and a bar here, and those may not be correlated at all, right? Because that would have to be 2 parallel lines. This could be one long line.
Right.
So he's just talking about this scenario.
This scenario, but also, as a control, this scenario.
Okay, that's a
Something
control,
like that.
all right.
Yeah, in different degrees.
All right,
but
so now so
roughly
you're gonna
that-
tell me about the difference between.
Yeah, so here you don't get phase synchrony.
Okay.
Here you get some, here you get a lot.
Okay,
So here's like, we would say it's like the same object.
Yeah, yeah.
So I thought that was really interesting because we've talked about voting across
Yeah.
cortical columns and so on, but we never really talk about synchrony.
Mm.
And to me, this is synchrony in our models is always really interesting because a lot of our stuff happens through active dendritic segments.
Yeah,
And so if you have a neuron and you have these active dendritic segments, in order for this segment to invoke an NMDA spike or to fire,
Yeah.
you have to be less than 5 milliseconds.
yeah.
Right? You have to have a coincidence of activity
Yeah.
within 5 milliseconds. And the best way to get that is through synchrony.
Yeah.
Right? This sort of, it's almost
So basically,
implied.
you're
right?
adding the idea of oscillation synchrony to the voting method,
Yeah, so
which is not surprising if you'd
it's
asked
not
me.
surprising because of this.
Well, not only that, but yeah, that, I just would have guessed it maybe for that, yes, but now there's evidence for it.
Right, and so this does not imply oscillation, but it implies synchrony.
Yeah,
But so here they're showing actual
Well,
oscillations.
it's pretty much if you're gonna have synchrony,
You've got to have oscillations. So I thought that was kind of an interesting
Yeah,
slide. So my question was to him, so this is great, but these are lines. What
yeah,
about actual objects?
yeah.
Right, so I wanted to find out about things like what if
Well,
what if you have this, but
and-
it's actually the same object.
Yeah,
Right? So, something like this,
yeah,
let's say a rectangle,
yeah,
and maybe one part is looking here, another part is looking there.
yeah,
But it's the same, they're orthogonal, but the same object.
yeah,
And do we see any evidence of synchrony? This is primary visual cortex
yeah, yeah.
of this.
Right.
Right? And so he then sent me the link to this paper.
This is related to, what's their names of their, up into the border ownership cell.
Yeah, it's very related. I mean, they don't look at synchrony, but it's very.
Yeah, I mean, in some sense, we would almost argue that the cat still has to know that this is a thing.
Yeah, yeah.
It can't be just some random, weirdo thing, but it might be, I don't know.
So he said they haven't quite done this, but they've done natural stimuli and looked at similar things like this. So I thought,
So, in the natural stimuli, you wouldn't just have big long lines, you have other things.
yeah,
But
so.
you have uniform objects,
Right.
Like coherent
Yeah.
things, not just dots.
Yeah, so what they looked at, and this is a 2013 paper now, so there's
Oh.
a big gap in between.
Yeah.
So they looked at are movies like this,
That's how this-
Branches.
branches, and then they presented stimuli they had two different movies, and they presented stimuli like this,
Just the two little image patches?
two patches, but they could be from the same movie or from different movies.
Uh-huh,
So they could be coherent or incoherent.
uh-huh.
So kind of similar to that. And of course, I got this paper literally 20 minutes ago, so I haven't really parsed through all of this, but they do a bunch of different techniques, but their basic conclusion, and I have to really go into it in more detail, is that when they're from the same movie and they're coherent, you get a lot more synchrony and a lot
Yeah.
more activity
Yeah.
than you would.
It's kind of an artificial stimuli in the sense that you're only presenting those patches. It's like those images, they show you like there's some circles and there's some lines in the circles, and then when the lines move, you realize there's an object behind the circles, so you're
Yeah.
going through a filter. It's kind of like that. It's not a
It is,
real
but, so they tried to control for this here, and I think that's what is, like how much context do you see? Do you see just a peephole, two
Mhm.
peepholes, or do you see some more
I
context?
see.
So they tried to control for that a little bit, and I need to read the paper in more detail.
Yeah.
But anyway, I thought this was pretty
That's pretty
interesting, and the
Yeah.
fact that any of this is even going on in primary visual cortex,
Yeah.
certainly is not consistent with the peephole model at all.
Yeah.
Which B level are they looking at, the B1 or?
This is V1, yeah. V1 and a little bit of V2, I think. These are in cats, which is
And this new
So-
paper is when, 2019?
2013.
2013.
Yeah, he complained to me, they published this in this journal.
Because it says updated
1000.
2019, so.
Access.
Data access.
No, this is,
No,
here.
Updated, yeah.
I don't know, that's a good question.
Anyway, 2000, go ahead.
Yeah, so he's saying this is a new research where it's very open and the review is open and everything like that. So they thought they would publish there, but it actually is not no one knows about it, so it's not getting much traction.
Trying to know about it, but it's not really taking off as they hope.
Yeah.
They wanted to build a platform without editors.
Oh, this journal is
This
not
journal,
journal.
yeah.
Yeah, so it's
Journal without
sort
editors, as far as
group
I'm
sourced.
recommendation
yeah,
engine
yeah.
that is built by peer groups of scientists.
Yeah. And he said, I think he sort of alluded it was a kind of a mixed experience from that standpoint.
That's
Unfortunately,
fortunate. I think it's a great idea.
it's a great idea, but it's going to take some critical mass and before it works. But anyway, I think this is an interesting.
So do you know in this new paper, are they still doing cats? And
Yeah,
are the
still
cats
cats.
still anesthetized?
Yeah.
No.
So there's no.
So that's good to know, because if these synchronizations didn't show up, I could argue that maybe it's because the cat's anesthetized.
Right.
But the fact that they do show up is still, then it's significant.
Yeah, in our model, this might be analogous to where we like grasp with a single touch.
Yeah.
And
Yeah, but
see
the
multiple
other thing is,
points of
it's
evidence.
also sort of like saying, when you're anesthetized, you're in a coma, some sensations on your, the cortex may not recognize anything. It's just, it's just like dead, it's like you're just passing information through. So it's very hard to know what happens when it's anesthetized. But if you see the results when it's anesthetized, it's still significant then. If you didn't see results when it was anesthetized, then you don't know why.
Right. Yeah.
So that's good.
Yeah.
All right. That's pretty cool.
So I thought that was
Yeah.
a little bit of fun.
This is interesting. Thank you.
Okay,
All right,
we'll move on to Lucas.
Lucas.
And I'll leave the paper up in case you want to refer to it.
The reason I'll be fast is that not because the paper is not interesting, just it's not very interesting for our research, I would say. So
You think this paper's not interesting?
no, the paper is interesting, but not for our current research.
Okay.
I'll see.
There are some touch points.
There are some touch points. I'll go through
the.
Can I?
Yes, you can.
So I'm just curious, if you don't think it's really relative to our research, why did you choose this paper?
Well, I chose before. I
Oh,
skimmed it and thought it would be a good paper.
okay.
I think it's relevant.
Well, it's relevant.
Okay, well, it's
It's not like
not,
I read
it's
it.
like saying, here's a neuroscience paper, I think it's absolutely nothing to do with what we're doing. Let's talk about
After actually-
the flies and
After I actually went down the paper, then
And I should remind everyone who may or may not be here, Thomas was an intern or a guest scientist. here
Oh,
for
that's
us.
that Thomas.
Yeah, that's that Thomas, yeah.
Yeah,
So,
yeah.
this is stuff he's been working on for many years before as well in a number of
when
different
was
contexts.
he a guest scientist?
2 years ago?
Roughly, yeah.
Yeah.
So this paper is actually from at the same time. So I just distilled the main concept in 2-3 minutes. So the main difference in his paper is, I distilled from the machine learning perspective, not from the neuroscience perspective. So this is a regular recurrent neural network. This is just the same recurrent neural network, and I just unfolded here. And the difference between the recurrent neural network and the regular one is that the output of the network is also the input for the next state, right? So this h of t here is input for the next time step. So this is between time steps. It's recurrent. And this is an LSTM, and you may not recognize because I've done some modifications, it's the same thing.
Okay.
I just took the memory out of the cell, and now I have the same recurrent neural network, but the recurrent neural network has a problem. And if you're learning several time steps in a row, and then you get a loss, you have a problem backpropagating that all the way to the beginning. So the difference, the way LSTM fixes this, it adds memory, and this memory is, along with the input, defines the output of that current time step. And that memory is modified, so you have 3 gates in an LSTM, and here you have 2 gates. One of them defines how much of that memory you're going to take into account. So this is like an input gate. And these 2 gates are the output gates, and they'll define how much of this memory you're going to forget and how much of what you learned here you're going to add to that memory. So basically, this line would be the long short-term memory, which is added to the recurrent neural network to fix that vanishing gradient problem.
I'm not sure if I follow. Does that mean that the memory itself sort of partially propagates through?
The memory partially propagates through.
Like does because it's not less like in
Right.
memory of the input and the output.
Right. So this memory is going directly from one time step to another, and we have these 2 set of weights. So what are squares or weights here, and they are defining at each time step what you're going to forget from your current memory and what you're going to add to your current memory. So forget and forget and something else. So these weights will be learned, and they will change the memory, but the memory is going to affect directly the next output as well, along with the next input. I don't know if that answers the question.
Does that mean that when I traverse from the output now backwards, I'm traveling back in time step by step, looking at those memories? So it's actually a temporal trace of some sort?
It's like a temporal trace. Imagine you have like a grammar where something now can affect something 10 steps later.
Right.
It's very difficult to keep this trace around for 10 steps in
Right.
a typical. So what these things will do is some part of it will recognize, oh, I need to remember this, and it'll artificially just keep it alive.
Right.
until the system says, okay, now you can put
But
it.
you don't remember everything. It's very selective.
It's
right?
selective,
It
yeah.
says that there's an algorithm saying, this is the important thing to remember.
Yeah.
And ignore the rest of the stuff.
And they'll just keep that memory alive for a long period
So
of time.
that's
until
some
it's
selection for an eligibility trace of sorts.
Yeah, you can say that. And these gates are the gates which will define what you forget and what you're gonna add to your memory stuff. And those gates are learned. So in LSTM, everything which is square here is a parameter. Everything here is learned. And
Is this your picture or is this came out of this paper?
no, that's my picture.
Yeah, that's your picture,
Yeah.
okay.
And I'm just parsing this paper through what we know of recurrent neural net. So there's a very different notation, I would say, in the way it defines inputs and outputs, and I had to. I was just trying to bring into this work.
Yeah, I don't know what this paper is about yet. You just described.
Right.
This
This is LSTM.
I understand LSTM,
Okay.
and you're saying, here's how I make a diagram of LSTM and a recurrent neural network,
Right.
but I have no idea what the paper's about.
So this is the paper.
Okay, so this is your background knowledge.
Right, this is the
and I want to
background.
go into what the paper's
Yes.
about.
And so the paper is represented in this diagram. So you got a recurrent neural network, and you also add a memory component here. And the memory component here is the head and trace. And
The what?
what he calls a head and trace.
Heavy interest.
And the way it's calculated, so the head and trace, it's the product of the pre-synaptic activation and post-synaptic activation. It's just the input and output. These are just the paper words. And the product of those are going to compose this head and trace. And this head and trace is updated from step to step. So from time step 0 to time step 1, it's going to flow here, and it's going to be updated with this correlation at that current time step. So you can see it's kind of similar to the LSTM. And the head and trace is also calculated. So you have the input times the weight plus the head and trace times an alpha. This is an alpha, which is also a set of weights that are going to define how relevant, how much you're going to take into account the head and trace into the calculation of your output. So similar to the LSTM, you have the input gates here. This alpha also acts as input gate. How much of the head and trace you're going to take into account in the output. And then after you have the output, you're going to calculate the correlation and update your head and trace for the next time step.
So in this case, there's no differential learning component about the update of the trace. It's like in the LSTM, the system decides what to at different times it'll update the memory and not.
Right. So
Here it's like it's doing it all the time. There's no gates here. There's no learning, right? So it's just going to have a continuous update of the.
right. So there is a learning rate here,
Oh, you
and
didn't
that's
show that.
the update rule.
Oh,
So
I
this
thought
is
that would be a little box. You didn't show that.
It's not.
Yeah, it's not a box. It's a parameter, but just like a little box, with like a little
Okay,
learning
but
rate.
it's, all right, but it's learned, but the moment to moment, it's always, I mean, if the learning doesn't change, it's always going to have the same update every time, right?
Yes. So the second paper, and you got to the point. So the second paper, the backpropamine, this small learning rate here, which is eta in these equations, it's switched by an actual gate. So it is learned.
Oh, okay.
So this is the neuromodulation part of it. So the neuromodulation is that this is going to tell you how much you're going to update of your head and trace at each time step. As before, you only had like this global learning rate. Now in the second paper, you have a specific gate as well,
Okay.
which is going to act like
Yeah,
this
okay,
gate.
all right.
So this is the backpropamine version of it. So this is the Hebbian update rule. This is the simple one, which is just a learning rate plus input times output, plus 1 minus learning rate and the previous head and trace. And this is the Ocho's rule. I was not familiar with that, which is another way of updating the head and trace. So it is both in the paper. He uses this most commonly and this in some of the problems.
What is the motivation behind this? Did they start off as saying we're trying to recreate LSTMs using backpropagation, or did they just did this independently of LSTMs, or how does the paper position itself in this field?
I was also curious about that. I'm not completely sure.
So I think part of the idea is that when you update the weights in a typical backprop network, everything gets the same learning rate.
Yes.
What he's trying to do here is to have some of the weights be more plastic
Got
or not,
Great.
as
So-
a function of.
Right, so I see
experience.
it. So that's sort of what I zoomed in on here. It's like the thing that struck me about LSTM is they have this sort of differential update for like what to remember is not always the same. And sort of cleverly figures out what things should I be keeping in the trace, not. I mean, this is how we, in our model, we have this context is propagated throughout. And we do this with separate representations at every separate point in time. Here they did something equivalent, but just by saying, this is the thing you need, this is the context you need to keep track of to know what to predict next. So it was clever, different. And so typical backpropagation, what I'm interpreting here, what you're saying is typical backpropagation has nothing like that. It has no idea of what's important and what's not important. And they're trying to add that idea to backpropagation. Would that be a good sort of assessment?
Do you mean this paper or this
Yeah,
paper?
this paper. It means, is that right? They're using backpropagation to make, it's no longer being uniformly applied all the time, right?
I actually failed to see how big of a difference is regarding LSTM. Both of them have.
No, I'm not saying it's different than LSTM. I'm
Okay.
saying it's different than standard backprop.
Right, it is, it
They're
is.
trying to make backprop more like LSTM.
Right.
And to me, the big difference is that backprop has no knowledge about what's important,
Right.
but LSTM has a concept of what was the important things in the past I need to keep track of.
Right.
Is that, I'm trying to ask if that's a fair assessment of this.
Yeah.
Okay.
And he's using coactivity between presynaptic and postsynaptic as a measure of.
Yeah, I don't understand why that works, but
Yeah, the main difference I think is this
Yeah.
traced line here.
I have no intuition why that's important.
It is because they're trying to store patterns, right? So that they want to use this for long-term memory of sorts. And so they're just using the heavy component for learning.
Yeah, but well, why? How is the Hebbian component going to provide this differential knowledge?
I should probably make a quick break just to say the kind of task they're using. So the kind of task is that they show a bunch of patterns to the network, and these patterns are shown like a bunch of times in a random order.
Oh, random order.
Yes, and then they give the network, let's say this is a pattern, this is a pattern, and this is another one. And they'll give the network just a degraded version of it and ask the network to reconstruct this pattern.
So they're not really doing anything in time. They're just doing pattern completion.
Which is what the paper was very much criticized for in the open review platform.
Oh,
Okay.
I mean, because the whole point of LSTM is to deal with time-based patterns
Yes. So
in context.
So that's what all the reviews focus on. I read through like 4 or 5 of them, just pointing out that like the idea is kind of nice, but they picked like the worst possible task for it because the whole point of an LSTM is that it can learn these temporal patterns,
Yeah.
sequences,
Okay.
and they didn't really pick a task where the LSTM can shine.
Yeah.
And even this trace implies that there's some temporal coherence or some temporal.
Right.
They
Yeah.
didn't.
Yeah. So that's a weird thing.
But of course, at pattern completion, the Hebbian component will do its job, right?
Yeah.
Just like it's
Well, that now I have more of an intuition why they're using the Hebbian piece there. And I was trying to understand how the relevance of that would be in time. I forget how LSTM does it, but it was kind of clever. I don't remember it, but okay. So that's really some of my curiosity or confusion about it because they're not really using it for a time-based task.
Yeah.
Which is odd. I agree with the reviewer.
Yeah, and in
That's
that case, I don't know why you use a moving average like that. You can just compute the average. If it's a batch thing, and it
that's
doesn't
right.
matter.
What's the point of having
You
time-based?
shouldn't really do a moving
As soon as
average.
you said they show these in random orders, I'm like, what the hell?
Yeah.
But in the second paper, there's a Nate's experiment, right?
I only skimmed the second paper because it's kind of sick this week, so I was planning to read it, but I couldn't.
But there's a maze task here.
Yeah, I reinforcement learning Nate's.
Maze as a M-A-Z-E.
But if you wanna,
No, I don't really, yeah, exactly. Just keep the paper and they.
So here, perhaps the temporal component
Yeah,
is more
exactly.
important.
And did they somehow take advantage of it here, or did they, I don't know. Well, it'd be interesting maybe to go over that sometime. I mean, the idea of building a temporally predictive model of the world is the core of everything we do. And so different ways of encoding time and prediction time and modeling sequences is interesting. So we have a model, and LSTM is a very interesting model too, which I don't think is really biological, but it works well. And so if this is a new way, I'd like to know it, but this doesn't illustrate it. Maybe the maze does illustrate it, but we'd have to get into the details of that. And in some sense, has been traditionally until fairly recently, this has been a backwater of all machine learning and neuroscience research. Dealing with time-based patterns, it just hasn't been people's focus.
One kind of loose connection to our HCM models, we have the notion of permanence. And the more coactivation you have, the stronger the permanence would be.
Yeah.
And so the less likely it's going to go from a 1 to a 0.
Yeah.
But if you're sort of in between, you're going to be right near the threshold, and you could easily go from 1 to 0.
Yeah.
It's sort of related to here. If the correlation between two units is very strong, the weights are going to be very strong and less plastic in some sense. So here, that's a kind of a loose relationship.
Okay.
I was wondering, I was having the same question on the paper, that it makes sense for this test. I was also not seeing how the head interface would help.
Well, I just assumed you're going to probably so temporal task when you started talking about LSTMs.
Yeah, I'm sorry. I should have started with that.
That was just my assumption.
Then it's like Vincenzo said, there's also this maze test, but I don't know if it's clear that the alpha propagation in the maze test. Did you get that in the paper? I didn't get that.
So the
Could you describe the maze test? Do you remember what?
I mean, do they always start the same starting point in the maze test, or is it try to win partial pieces of it?
No, the endpoint always changes. So the endpoint's like always randomly placed. So at each episode, it just restarts at some point in the maze.
Well, I guess
Or the starting point is?
we have to walk through the entire thing. I mean, what is the maze task? I don't have no idea what the maze task is. Is the maze changing? Is it the same maze? If you move the endpoint, then what the hell can you learn?
No. So the maze is fixed, but they're changing the endpoint.
But well, how can you learn? And does the maze look like that? It's not really a maze at all. It's just like a.
Yeah, that's the maze.
That's just an XY,
And that reward. So one of those points where the reward is, and that point's always changing. So
then they train for a while on that particular one, where the reward is some spot.
the reward's at spot, and that spot is always changing.
So they set up the system where they put the reward in one spot. They put you start in the same spot, and then
And the reward changes every time.
But it can't change every time. There's nothing to learn.
Well, you have to learn how to navigate in this quote unquote maze.
But how could you learn to navigate? I guess the point is, you can't. I guess you'd say you just don't go. You wouldn't go back and forth, back and forth, back.
Yeah.
I mean, if you change the location of the reward, then you essentially have to do a sort of random walk to find it. So
No, I think it's given, you know where you are and you know where the reward is. How do you get there quickly?
As quickly as possible.
Yeah. So it's not like the reward is hidden.
How do they specify the locations?
Probably that might be the input.
At each episode, one reward segment is randomly chosen as the reward location. When the agent hits that location, it receives the reward and is immediately transported to a random location in the maze.
It's a random start and then a random end.
Right. So that is an episode that lasts 200 time steps, and then I guess they have multiple episodes.
So how does the network know your location? What is in some sense, the reference frame of the network? What is the input of the network that says, oh, I am here?
Yeah, generally, it is a matrix in which you have, 3 possible entries: yourself, the food that you're trying to get, and nothing.
So I mean, this is represented as an XY set of numbers.
So here it says the input.
It's a 3 by 3.
Yeah, there is a 3 by 3. 2 by 2 neighborhood center on the agent.
So again, I'm imagining some neural network. Am I feeding in 3 numbers into the neural network?
No, 9.
Nine
It's a 2 by 3. Yeah. Just saying it's a 1 or 0 either.
So it only sees a local neighborhood. It doesn't see the whole maze.
It sees its options that it has, right? It sees wall segments and itself and the segments it can walk into.
Mm.
So it's like an autonomous robot with very limited vision, right?
So does it, I'm with Jeff, I'm just trying to figure out is it trying to, how do you tell that this is the goal? How is that set up? You only can see the local coordinate, you don't have a master map of the whole thing.
Right, but that is the whole point of this task, right? To back propagate the reward that might be given much, much later after that agent roams around that thing to find that reward location.
So was it learning a search strategy?
No.
That must be.
Yeah, it's learning a policy, I'd say. I'll just add that the input is not just the neighborhood, but also the previous action. So
Yeah, it must be learning just not to go back on its own
So
self.
I look at these kind of problems in two ways.
yeah, exactly.
It's just-
You can have like a rat solves a problem like this. A rat solves a problem by building a reference frame for rheumatin, but grid cells and place cells, and learns a map of this world, and then uses that map to calculate how to get someplace.
Right.
Or it could be like a bacterium. A bacterium has a strategy. It goes forward, and then it turns more often when it doesn't find what it's looking for.
Right.
And this is more like the bacterium, I think. It has no idea where it is in the maze. It has no concept of the overall structure. It just has a few things it can do,
Sounds like.
and it's coming up with a strategy. Marcus, you should have.
Well, this could do the map thing. I mean,
Where is the map represented in this thing?
In its own activity, in the recurrent, it could develop a strategy where it just doesn't go back on itself.
Yeah, but that's like the bacterium saying, I'm not going to turn randomly. I'm going to turn with the various. The bacterium doesn't know where it is in the world. It has a strategy for movement, which is successful.
Well, you can derive strategies from this, right?
Yes, but it doesn't know where it is in the world. My point, I'm trying to put this
so
binary.
like that's the task. Like Lorraine was saying, like after 200 whatever iterations, it resets. Then the reward changes, but the reward location is in the same place again and again, and it's being randomly teleported somewhere. So its task is A, represent what is the location of the reward using the memory of the LSTM. B, localize yourself. C, figure out how to get from
Does
yourself.
does the network actually contain that information?
It's been given in theory, it could do all
Because it could also, in theory, but I'm trying, there's a big distinction in my
of that.
mind.
It's being given all of it.
Yeah, but does it represent that? Could it could also learn the task as in, given these set of parameters, I just know that these set of, I move this, and I get there. Without actually having any concept what the overall structure is. In the same way that a bacterium gets to the reward, it has no idea what the overall structure is. So maybe I'm wrong about that,
Yeah, I
but
don't know what it's doing in practice. I'm just saying it is in theory, an ideal model could do, given the inputs.
it could, maybe.
Yeah.
But
So in
given
order to, a model which learns the ideal scenario is going to do better than the bacterium scenario. So if it's really minimizing its error, it's going to.
no, but I think this could be an advanced bacterium. It says, oh, not only do I just turn less often when I'm getting my reward, it says, given this set of inputs, I should just follow this pattern, bling, 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 and it made me actually know, just like a deep learning network can recognize an image, it has no idea what that image is. It just labels it. And this might just come up with the right pattern to solve the problem without having any deeper knowledge of what the problem is. I'm not meaning it as a criticism. I'm just trying to understand what this thing is capable of.
Well, you can arrive at policies, right? For example, of not exploring every column or row, but every other column or row.
Yeah. And that's a policy. A movement policy is not the same as knowledge of the environment. It's just a movement
Right.
policy. A bacterium has a movement policy.
I mean, I have an
Yes.
early model of Roomba, and the thing is incredibly dumb, and it doesn't quite work. But basically, it goes and hits something, it always seems to go left, a certain amount, and it basically falls into oscillatory stages, and then sometimes has to be helped out, sometimes it finds its way around because of, but the point of it is.
Well, we don't know what a room is doing. They could easily implement an X, Y coordinate
It
system.
could have, but it doesn't seem to.
Well, we don't know.
Yeah,
Maybe they just did a bad
whatever
job.
policy it uses, it really sucks.
You're right. I'm just saying
Sorry.
that there are things out there which have blind policies that try to explore a space without any knowledge.
Of course, that's right. There's
whatsoever.
nothing wrong about being a bacterium.
Sorry, Roomba.
Said
early stage, early generation.
Well, they do show here that the differentiable plastic networks do dramatically better than the simple RNNs, which they say here get stuck.
Yeah.
Well, but the simple RNN, not the LSTM. I don't see a comparison to LSTM.
Well, did they have it out? Yeah, good point.
Well, is that like an argument that it doesn't fall into some kind of valley where it can't get out of, and that it continually kind of refreshes itself and tries new things? Is that what the plasticity gives it?
The thing is, this is also just a small
No.
part of the whole paper, right? I mean, this is like barely 2 paragraphs. And then they move on to
What's the title of this
next,
paper?
next task. Right?
What's the title of this paper?
So this is differentiable plasticity, the one we're discussing.
Oh, that's the same one. I thought you were saying the mains was a different paper.
No, but
No,
there's
the
there's a second paper, the backpropamine. That's the
Oh,
one
oh.
Florian's talking about, right, Florian?
Oh, so this is not the second paper. I thought we switched to the second paper. So the maze is in the first paper. It's
It's
a
in
small
the
part
first
of the first
paper,
paper.
What's in the second paper too?
It's in the
Okay,
second.
but we're looking at the first
But
paper.
it's a different plot.
Well, that's kind of the same.
That plot looks
Plot.
much less difference
Okay.
between the
Okay,
two. Anyway.
witching hours arrived. I'm gonna step out.
Do something more black.
So do you wanna go through some of the other points as well? On the second paper, is have more stuff.
Well, I don't. Not particularly.
Yeah.
I mean, I mostly paid attention to like the way they apparently like I'm used to having my weights be Hebbian weights. I mean, somewhat optimized Hebbian weights because of Bayesian weights, but it's really normalized by the prior and the posterior. But here it's sort of an additional component on top of a weight which depends on this LSTM mechanism, which I'm not all too familiar with.
Well, his thing doesn't depend on the LSTM. His is purely Hebbian.
But it does learn this alpha and then it learns this.
Right.
Yeah.
It doesn't, maybe you can think of it as gates, but it's a fairly simple, it's much simpler than the full LSTM.
Yes, it doesn't have that complex mechanism inside
No,
the
but what I mean is
You can think of this as, maybe it could encode some short-term memory of some sort of where it's being. And so, it could learn that certain weights should be, much more important right now than others at points in time.
If I got that right, so the idea is that you still, in this paper, they still use backpropagation to time, right?
Yes.
To learn
Yes,
the
yes.
basic LSTM algorithm. Then they use just this Hebbian rule
Right.
to have the parameter, let's say plastic parameter, to modulate somehow learning through time of these.
Right. Just one correction. They don't use an LSTM, they use an RNN and then add the Hebbian component.
Maybe in this second paper they use
Maybe, yeah.
But in any case, I think this idea is very similar to what we have seen in continual learning in general, where you want to find somehow the importance of each weight and preserve that with respect, to changes on the same weights. So I guess this is just, and it was shown somewhere else that you can estimate the importance of a particular synapse weight. Just looking at the pre and post synaptic activations. I mean, essentially the two neurons, this weight is connected,
I
right?
think you're talking about the fast weight paper.
No, I was talking about it's called the memory aware synapses paper, and in that particular paper they show that you could somehow estimate the importance of a particular weight just looking at the pre and post synaptic activations, and so it's kind of similar. I don't know why they didn't compare their techniques with other, standard continual learning techniques. Essentially, they are doing similar things. It was curious to see that in the second paper they just compared with standard, LSTM variations. So it was.
So if you scroll a little bit down in that paper, right, and you get to the, where is it? Use equations.
To the equation.
There's 3 methods.
Oh, way down.
No, in just the method section, chapter 3 on that paper. Sorry. Yeah. Right. So they have a fixed component in green, and then the modulated Hebbian component, which has this learning rate beta, right, in the second time. And so what was a little bit confusing to me at first was the fact that I'm used to my weights being the Hebbian component, but here
No, it's just
Exactly, but here, of course, they have the weight, which I guess is a component of this LSTM.
Yeah.
And then they add sort of a Hebbian component to it with some fraction of
Wait, okay, so here there's no LS, without the Hebbian component, it's just a standard recurrent.
Yeah.
Yeah, just
Was
So-
I thought that was
Right,
was I thought it was.
right.
Yeah, there's no, without the Hebbian, it's just pure recurrent network, no LSTM in there.
Right, and
And
that's
then they add
understandable because the Hebbian component cannot learn temporal patterns, right? Unless you build a different kind of a Hebbian learning rule where you have an eligibility trace and you have like a lagging component, for example.
Or HTM temporal memory.
Or an HTM temporal memory, or any of the other very awesome frameworks, right? So, yeah. But yeah, I mostly just thought the name was hilarious.
Yeah. What I'm not clear about is this alpha parameter here. How is that?
These are the gates. This is
These
here.
are the gates.
These are learn, yeah.
These are learned?
These are these guys. Alpha.
And what would that actually be?
Yeah, it would be the input. The head and trace gate, not the input, the head and trace.
Hebbian
gate.
trace gate, but this is a static thing. It's not dependent.
No,
on
these
any-
are learned through
Yeah,
back
it's
propagation.
learned, but it's not dependent on any input.
No, it's depending on the head
That's
system.
just
Do you understand right that if you had patterns that were very static,
Right.
then you would expect that alpha to be very big? Because
Yeah.
it would, like, a lot of the activity would be explained by just the
Right.
correlation with
Yes.
itself. Whereas if you had highly temporal patterns that were super fast changing, you would expect that component to go to zero essentially.
I would expect the opposite.
Oh,
The
that's
thing is,
interesting.
if it's very static, you don't need this Hebbian component at all. You can just do static recurrent nets and it'll be fine. So you don't, this
But
thing
to
will go to
me, the
zero.
Hebbian component is the static component.
If it's static, like you're always showing the same thing, then there is value in the head and there's more value in the head and trace because you're always showing the same thing.
If you're always showing the same thing, a recurrent net can learn it just fine. You don't need the Hebbian piece.
Right. I mean,
So,
I'm getting an extremism, but
Oh,
somewhere
but to
in
me,
between.
the recurrent component is the Hebbian component. It's fascinating how these different philosophies are. So
no. So this is that is a recurrent component, but this is embedded in a traditional recurrent net,
right,
which is also recurrent. So what this weight is, so if you use Lucas's old diagram,
right,
this self connection here,
right,
in here, these are the WIJs,
right.
and these are static numbers, right? This is the
No, yeah, the weights are the bugs. That's what you're saying, right?
correct, but it's applied to this input.
Right.
Yeah.
But these
So
are
this is so
recurrent.
these are recurrent weights. The weights for the recurrent connections.
Right,
So if you think about, if I draw a bunch of units, they're all fully connected here.
right.
Each
So you
one has a
can learn
WIJ.
autocorrelations.
Yeah.
I mean, you can learn static patterns.
Yeah. So if you can learn it, you don't need the Hebbian.
But then there's a weird redundancy, then I don't fully understand what the Hebbian component actually adds in terms of capability.
I think
It's decide which weights to preserve and which weight you can change fast, they're not usable.
Yeah. So these weights here are learned, right? And they're always static. They're not dependent on the inputs at all.
Right.
Okay, so these are learned using a data set, a training set, and you come up with the optimal weights here.
Yeah.
And then for a given input sequence, then the only thing that can change is this Hebbian component.
Right.
And so this thing can say, okay, if I'm seeing, let's say this alpha is really high, then if I'm seeing a lot of correlation between this guy, and this alpha is high for this connection, I'm going to pay a lot more attention to this connection. And if this guy alpha is really low, I'm going to pay less attention to this for this specific input trace. Right? So the Hebbian piece can be very dynamic and dependent on the input thing. For a static case, you just don't need it at all.
So it's almost like an auto tuning feature that you have this base
Yeah.
network there, but then I still want to have something, if I'm being fed something different, I want to have some way of adapting to it, and this is a mechanism to at least partially do that.
Right. And so, it's clearly more powerful than a pure recurrent net because you have an additional set of parameters.
it's not clear to me how more powerful than an LSTM because
But then an LSTM,
alpha,
sure.
alpha is still static. It's
Yeah, yeah.
and then eta is also static. The only thing changing is it's the trace. But in
Yes.
LSTM, we also have the trace.
Yeah,
We also
so,
have the
yeah.
So it's not clear to me how.
Compared to, I think his argument was that it learns a lot faster.
It's a way to do that detection, right? The role of dopamine is not to signal reward. It's to signal reward prediction error,
Yeah.
right?
But none of that is here.
If you recall dopamine, projections like the projections of substantia nigra and the basic ganglia, which do this, right? You get dopamine release when you withhold the reward that would be expected. So dopamine is not a reward signal.
Right.
And so you wonder how this applies to this, right? So how would this network recognize that what it sees is not what it expected to then upregulate plasticity? I'm not sure.
Yeah, they don't really have any sort of reinforcement learning. Oh, maybe.
I think what the point of the dopamine is the neuromodulation is here. It's in the eta. So eta is going to control how much of the output here how much of this actual co-activation you're going to use to update your trace.
Right, how quick the Hebbian component updates.
Yes, that eta is going to. So
How does that help?
so that would be the dopamine part of it. So.
Well, it's not really dopamine. It's
Yeah.
dopamine is more prediction error.
But I mean, as in the paper,
Like with the idea that it is a chemical component that can affect somehow the plasticity of the ways that
Yeah,
are
but
not all the same. They have different importances and.
Yeah, but what Florian is saying, that's true, but it's triggered by reward prediction error. So if you're expecting a high reward and you get a high reward, you're not going to get much dopamine. But if you're expecting a low reward and you get a high reward,
Yeah.
you get a lot of dopamine.
The very basic reasoning just being that, when you're off in your prediction, your network is wrong. So you need to change.
Yeah.
Whereas if you were right to not expect a reward, and if you were right to expect a reward and you got it, there's nothing you should change. Nothing.
And it's the same, it's a very tight correlation with temporal difference learning.
Right, that's
yeah.
the dark side idea.
Yeah. So that would be a great topic for a future journal
Yeah.
club, I think, just exploring that, or even the meetup. I think that's really good. Okay.
Yeah, so it's maybe a little bit sad that you do this wonderful, awesome term. Dopamine, but then they don't really understand what
There was
dopamine is and
a
what it
sentence.
Yeah, so he should have,
have.
so the feedback is he should have left this term for an even more awesome paper.
does. Yeah, yes.
All right.
Because, they treat this as just neuromodulation, but the dopamine is very specific, kind of a neuromodulation, right? Not anything that is, not anything that is neuromodulatory is dopamine. But okay, good.
Yeah.
Fine. So does anybody know Uber AI Labs, what they do?
Yes, why don't we stop the live streaming?
Right.
Okay, just a moment. I'm going to stop the live streaming. Okay, you're good to go. You're not being streamed. Okay, just want to say thank you guys for watching, and hopefully you'll tune in for our next live stream next week.